Hey everybody, Mr. Ellinger for video 2, and this one is specifically about substitution. So the stuff in this video is stuff that everybody needs to know. We'll show you an example of an AP problem, and these are this is going to feature some problems where substitution is in some cases is required. So if you're like a huge Lindstrom and chain rule backwards fan, you still need to know this stuff about substitution. Okay, so some integrals Lindstrom can't even be done, and you got to use substitution, but it's a little more complex than the ones we've seen before, and this is the example one we have. And the problem we have is that we can't do any algebra. There's no simplification we can do. We could make u equal to 2x plus 1, but then the du wouldn't help us with the x. And so our inside-outside look doesn't give us an idea about what to make u, and so we're kind of stuck on this one. Turns out there's a way to do it, and what you do is you still make u equal to 2x plus 1. And so du is 2dx. Okay, cool. And so let's see where we're at. So we've got this part here becomes square root u. And the dx, I can solve in this one. So that's du over 2 is dx. So I can do the du over 2 here. And then I still have this x thing. Like that was the whole point of this problem, was that this x thing is a pain here because I can't take care of it with chain rule ideas or derivative of the inside ideas and stuff. Well, this is one of those problems where you do what might have occurred to you at the very beginning of doing substitution, which is to solve for x in this equation. So x is equal to, so let's see, subtract the 1 over, so it's u minus 1 divided by 2. And now you can plug this in. U minus 1 over 2. And you might be like, okay, well, why was that helpful, Mr. Ellinger? You know, like, okay, now we've got this u integral that we're dealing with, and how are we supposed to do this one? Well, keep in mind, these are constant multiples, so I can bring these constant multiples out to the front. I'm going to continue over here, just so I'm not like trying to squeeze in this little space and then going over here because I'm going to run out of room. So I can bring the 2 1/2 times together and make it 1/4 in the front, and then I've got u minus 1 times u to the 1/2 du. That square root of u becomes u to the 1/2. So if you look at the original problem and you look at this problem, you might not notice why the new problem is better. And the reason why is because now we can simplify it. So in the original problem, there was no way to distribute the x, but here I can distribute the u to the 1/2. So it's 1/4. I still haven't integrated yet. U to the 1/2. Oh, whoop, no. U to the, whoop, wrong pen. So I got one pen that's erasing right now and one that's not. So it's u to the 3/2 minus u to the 1/2. U to the 1 times u to the 1/2 is u to the 3/2. All right, and so now I got this, and now it's all set to anti-differentiate. So it's 1/4 times u to the 5/2 with a 2/5 in front minus u to the 3/2 with a 2/3 in front. Plus c. You could distribute that if you wanted to. I'm just going to leave it as is. But the one thing you have to do is you have to put the x's back in. That would be required. So I might as well distribute it. So 1/4 times 2/5 is 1/10. So it's 1/10, and u is 2x plus 1. 2x plus 1 to the 5/2 minus, 1/4 times 2/3 is 2/12. Wow, that's 1/6. And plug in the u. 2x plus 1 to the 3/2. Done. Okay. That's the last substitution example in terms of, I just want to show you an example of one where the substitution isn't obvious, like the du doesn't take care of everything, but you can try a substitution and you end up solving for the variable and substituting in for everything. It's a pretty uncommon problem, but it could show up. No harder than this one. This is about as hard as it gets. Okay, now we're going to go to definite integrals. All these so far with substitution and Lindstrom have been indefinite integrals, and now we're looking at definite integrals. And so the question is, how is this? That's where you have bounds, And so you have an area, you'd have no plus C, and the answer is going to be a number. So how is this different? I'm going to do this with substitution. You can do it with Lindstrom, but I just want to emphasize stuff with substitution. So I'm going to do substitution on these ones. So what's the choice that you have? Well, choice number one is to do the entire problem in U, and choice number two is to do U just temporarily. Let me show you what I mean. So I'm going to do the whole problem in U in this one. So I'm going to do U equal to 5x plus 1. du is 5dx. And so I'm turning this problem into the integral. And so I have to turn this into U as 1 over U. And then dx is 1/5 du. But now I've got new things that are also in x in the original problem, and they have to change to u in my problem. That's the bounds. These stand for x values. We're going from x equals 0 to x equals 3 and finding the area under this curve. Well, now we're not using x's anymore. We're doing u's. So we can't put a 0 and a 3 there. We can't know that it's 0 and 3 because those were x values, not u values. So if I want to switch it to u's, I have to switch everything to u's. And so how do I turn that? How do I do that? Well, I say, well, when x is 0, u is 5 times 0 plus 1. I just used my equation that tells me how to turn x's into u's. So u is 1. And when x is 3, then u is 5 times 3 plus 1, so that's 16. So now this problem has become this. It just looks a lot different, but it's 1 over u times 1/5 u from 1 to 16 instead of 0 to 3. But you can kind of see it if you look at this problem. I mean, we've got this stuff in order to do the antiderivative, but notice that like when you plug 0 into this function, you end up getting 1 over 1, and that's what would happen here. And when you plug 3 into this function, you'd get 1 over 16. So I hope you can see it's like, oh, it's like we're plugging in 0 and 3, but that means that if this is just u, then we have to change it. All right, so now we can do the problem. The antiderivative is 1/5 natural log of u evaluated from 1 to 16. And I can plug the numbers in. 1/5 natural log of 16 minus 1/5 natural log of 1. Natural log of 1, big 0. And so it's 1/5 natural log of 16. So this is the big idea with definite integrals, is you have to change the bounds also. But I said you have a choice. Technically, you actually could do this a slightly different way. You could instead, watch my time, you could instead take the antiderivative, just use u substitution to figure out the antiderivative, and then go back to the x world. I'll show this once, but I'll show you an example problem in just a second where you have to stay in the u world and do everything in u like we did on this problem. So what I could do is I could say, well, what's the antiderivative of 1 over 5x plus 1 dx? And I could do the same substitution, so you can copy the stuff over here. And so that's 1 over u times 1 over 5 du. And so it's 1/5 natural log of u. And I'm supposed to evaluate that from 1 to 16 in the u world. But I could go back to the x world. I could say, oh, all right, let me go back to the x world. In the x world, that's 1/5 natural log of 5x plus 1. And so I just used the u's to figure out the antiderivative, but I went back to the x world. And so I could evaluate this from x equals 0 to x equals 3. And so I use u substitution as a trick to find an antiderivative, but then I don't stay in the u, using u's. I go back to x's and then plug the x's in. Or you could just stay in the u world and change the bounds and plug the new bounds in, because they have to be updated because now you're doing everything in u. All right, I want you to try Based on the video time, I only want you to try one. I want you to try this one right here. No, let's do this one. I want you to try this one. You can use Lindstrom or substitution, your choice. No, let's do substitution. Sorry. I want you to do substitution on this one so that we can have this U thing. And you can do U's all the way, or you can go back to X's, either one. I'm going to pause the video just for time. And so you should try this one yourself. Okay, I haven't quite finished it, but I'm close. And so I did U equal to negative X over 2. I did du and then solve for dx to plug that in. And so here's my, negative 2 du. Wrong variable. I had it right down below. But now the thing is I have to make a decision. Am I just going to do the antiderivative and then switch back to x's and plug in the x's, or am I going to change the bounds and solve the problem in the U world? I'm going to do it the second way, and you'll see why in an example problem. But either one will give you the exact same answer. It's your choice. So I'm going to change it. It's now U equal to 0 to U equal to negative 1/2. You don't have to write the U's in there. I'm just doing that for emphasis. Like, this is x equals 0 to x equals 1, and now the new integral is U equals 0 to U equal negative 1/2. All right, and so the antiderivative, just bring the negative 2 in front, is negative 2 e to the u, evaluated from 0 to negative 1/2. Whoop. And now plug the numbers in. So it's negative 2 times e to the negative 1/2, plug in negative 1/2, and then plug in 0 minus e to the 0, which is just 1. And you can distribute that if you want to, or I'll just leave it like that. Yep, that's the answer on this one. This one was fine. This one's a little tricky. You make u equal to sine x, because then the du gives you the cosine, and that takes care of this. This is cosine x times sine of x. We're not going to do this one, but you can try it if you want to. I can put the answers up. Finally, this last one here, this is a multiple choice problem. This is an example of an AP problem. And notice they've told you have to use this U substitution, and they've said you have to use the substitution in here. And notice all the answers are in U. They didn't go back to X's. So now you have to decide what would the new integrand be and what would the bounds be. And the bounds, as you see, are going to change because now it's not from x equals pi over 6 to x equals pi over 2, but from u equals something to u equals something. Go ahead and try this one out. This is straight off an AP, so this is like the kind of thing that you would expect to see. I'll pause it in a second so you can try it out. Okay, so you notice they all had u to the 5th in the end because you had sine to the 5th 2x right there. And so anyway, u is sine 2x, and so this is sine 2x to the 5th, and so that's u to the 5th. And then I solved for cosine 2x dx because that's all my other stuff, and so that's my cosine 2x dx here after I did my du. And then I solved for cosine 2x dx. So that's 1/2 du. Oh, I could see they were trying to mess with me. So A is wrong, looks wrong, and E looks wrong because I want a 1/2 in front. Okay? And so this would be a 1/2 du. But now I got to check my bounds and make sure my bounds are right. So it's when x is pi over 6, then sine, I should say u equals. I'm going to make it. U is equal to sine of 2 times pi over 6, so that's pi over 3, which is square root of 3 over 2. Oh, this is basically like a trig value exercise here. And when x equals pi over 2, then u is the sine of 2 pi over 2, which is pi, which is 0. So it's option D because that goes from square root 3 over 2 to 0. That's what you get when you plug x equals pi over 6 and x equals pi over 2 into the formula for u. I finally put a just a little summary here of the ideas. Just reverse chain rule is the easiest, but the Lindstrom technique is a way to get a problem into reverse chain rule format by multiplying and dividing by a constant. And you can always use U substitution. If it's clear or if you like it better, I will not complain at all. A few problems actually require U substitution, but they are less common. Okay. There's one more video on one kind of problem, and sorry it's a long day. See you soon.